Now that we've looked at solving a rational inequality by graphing, we want to look at the algebraic method for solving these types of inequalities. Again, we're going to have to do this on the final exam and on your homework, so make sure that you can show these steps. Being able to do the algebraic method is much more reliable than doing the graphing method for the reasons that we've talked about before. Your first step on solving a rational inequality, again, is to make sure that that we're comparing to 0. It doesn't do any good to compare to 3. Now, if I was graphing this, then I could be a little bit more lenient on that. Algebraically, you have to compare to 0. So let's subtract the 3 from both sides. And then in order to compare to 0, we need a single term over here, which means a single fraction. We can't compare two terms at the same time. To combine these terms into a single fraction, we have to have a common denominator. And our common denominator has to include all the factors of each of the denominators. Of course, a factor of 1 is just understood, so we don't have to write that. But we do need the factor of x plus 2. This first fraction already has that denominator, so we're not going to change the numerator at all. We just rewrite it. But this second fraction needs to have a factor of x plus 2 in the denominator, so we can multiply to get that, but we also have to multiply the numerator by x plus 2. When you do that, take this negative with the 3 and just distribute it through that factor, so negative 3x and then minus 6. Again, that's greater than or equal to 0. Now in the numerator, we want to clean that up, and you can see we have 4x and negative 3x, which is x, and then 5 and negative 6 is minus 1. So this simplified to a really basic rational inequality. Sometimes you're going to have more factors than this, but the process that you follow is going to be exactly the same. So this is our inequality. And the first thing we want to do is remember that we can have a change of sign not only at zeros on rational functions, but also at the vertical asymptotes. So we want to draw our number line, and on the number line we want to put the zeros of the function and the vertical asymptotes of the function in order. The zeros of this function are going to come from where the numerator is equal to 0, and that's going to be at x equals 1. And the vertical asymptote is going to happen when the denominator is equal to 0, so that's going to be at x equals negative 2. So we put those on our number line, and that divides all of our real numbers into 3 intervals. And just like on our polynomials, we want to test each interval with all of our factors. When we have a fraction is going to be positive if you have the same sign on top and the bottom. It's going to be negative if you have opposite signs on top and bottom. So I want to take every factor of the numerator and every factor of the denominator listed on the side and test it. If I get an odd number of negatives, then overall those y values are going to be negative. If I get an even number of negatives, then overall the y values are going to be positive. So if I test a number that's less than negative 2 in the first function, I'm going to pick negative 10. Negative 10 minus 1 is negative. Negative 10 plus 2 is negative. So if I have a negative factor over a negative factor in my fraction, then overall my y values there are going to be positive. Go to the next interval and do the same thing. Pick a friendly number between negative 2 and 1, like 0. If I put 0 in for x, then I have a negative factor there. If I put 0 in for x in the other factor, then I get a positive. If I divide a negative factor by a positive factor, then my y values are going to be negative. Then pick a number that's bigger than 1, like 10,000. 10,000 minus 1 is still going to be positive, and 10,000 plus 2 is going to be positive as well. If I have a positive factor divided by a positive factor, then my y values are going to be positive. Look back at your problem where we compared it to 0, and you see that we're looking for greater than or equal to 0, which means that we're looking for the positives. So we're going to shade this interval. and we're going to shade this interval. Now we have to be careful on rationals that we never include vertical asymptotes as part of the graph. So even though we have an equal sign here, we're going to include where the graph is equal to 0, which is where the numerator is equal to 0 or x equals 1. So we can have a square bracket there. But the -2 that we got was where there's a vertical asymptote. So whenever you think about it, as soon as you think about it, make sure you make yourself a notation that you're not going to include that -2, because it would make that denominator 0, which of course is illegal mathematically. So now that we have our number line, that represents our solutions. We just need to write it in the correct notation. So let's use interval notation and go from -infinity until we get to -2, parentheses so that we don't include the -2, and then brackets on the 1 because we do want to include that, and then infinity. Remember that if you don't have an equal sign on your inequality to begin with, then you will always use parentheses all the way through. But if you do have the equal sign and it's rational, do not include the values that cause the denominator to be equal to 0. So that's our solution for the rational inequality algebraically.